Okay, this is problem 4.14 from Hagen. It's another static equilibrium problem. Okay, so our process has been to get started with a free body diagram. So I'm looking at this. We have a 250-pound mass box held in place by a cord. There's a spring scale on it. Of course, spring scales read force, basically. And if all the surfaces are smooth, what is the reading on the scale? All right, so first of all, you have to make an assumption about what it means to be smooth. All right, so the idea here is that smooth implies that the friction on the plane that opposes the motion of the box is negligible. So we don't need to draw in friction forces. Okay, so the first step has been, let's do a free body diagram, and so we draw a rectangular shape for the box, and we know that the box has a weight W. We can calculate that because we know that weight is mass times gravity. Okay, we also know that there's going to be a normal force to the plane. Okay, so this is 90 degrees to this. I'm going to draw this in red. Here's the plane. Okay, so we know this is 90 degrees to that plane, and this is the normal force. Okay, and then we have the tension force acting on the box. Okay, that xt, and we know that angle also is given to be 20 degrees. All right, so there's a picture. All right, and so we're looking at this and we're thinking, well, we need to figure out the equilibrium equations that would model this problem. Okay, so let's get started with that. All right, so what we know is that sum of forces in the x direction have to be 0, and we take the x direction to be to the right, being positive. Okay, so I see that if my coordinate system is right in line with the page, all right, so I'm going to draw the coordinate system in green. Okay, so if we just use the normal coordinate system x and y, you could put the coordinate system parallel to the x-axis parallel to the plane, but let's just go with this. Okay, and so what we know is that the weight doesn't have any horizontal component. But the normal force does. All right, so we need to figure out what is that angle that the normal force is acting at in order to get the horizontal component of that. Okay, and so we do a little bit of geometry. All right, so if this is normal to this plane, wouldn't it be true? Can you tell that this angle right here in purple, the purple angle, is also 20 degrees. Okay, so once you know that, all right, we can then write that the component of the force acting, the normal force acting in the x direction, would be in cosine 20 degrees. Actually, wouldn't that be, that would be sine, right? Because it's the opposite, the 20 degrees, it's hard, I didn't draw that very closely, but the 20 degrees applies here. Let me change it to purple. Okay, so that's the angle that's opposite. I mean, the side opposite is the normal force that we're looking for. Okay, so you would use, in this case, sine. Okay, and this moves in the negative direction, so you need a minus sign on it. Okay, then we resolve the t vector into its horizontal component. Okay, so right here, that would be t times the cosine of 20 degrees. Okay, the weight is not acting in the horizontal direction, so this sums to 0. Okay, so there's one equation, and so I'm asking myself, all right, what's unknown? I don't know n, I don't know t. So I'm going to need another equation. Okay, so in this case, sum of forces y equals 0, with y being up to be positive. That's what I'm going to use. Okay, so I immediately see that the normal force, I'm going to draw that in red again, acts up. All right, and so I can resolve that. That would be the adjacent side of that 20-degree angle. Okay, so I would have, since it acts up, it's going to be n cosine, because it's adjacent, 20 degrees. Okay, and then for the sine component, all right, so the vertical force of the sine, okay, right there, that would be, you know, the side, you know, you can visualize it being moved, you know, over here. All right, so that's the vertical component. All right, so that's opposite of the angle, that's why I moved it. All right, and so that would be plus, because it moves up, t sine of 20 degrees. And then minus w, because we have the weight working down, equals 0. Okay, so now we have two equations and two unknowns, and we can solve those. All right, so what I have, I could gather the terms up and put this in the form, and we talked about Cramer's rule. I wanted to show you that. Okay, so we have n's, and the coefficient out in front would be minus sine 20 degrees. Okay, and cosine 20 degrees. All right, and then we have plus cosine 20 degrees times t sine 20 degrees times t, and then I move everything, all the constants, to the other side. W is known. Okay, so W was 250 pounds mass, so that's pound mass. Convert that to pound force, you get 250 pound force. Okay, all right, and so that gives us the equations. So at this point we have two equations, two unknowns, and we can use Cramer's rule to solve for the tension in the cable. That's what we're asking for in this problem. So T is equal to, according to Cramer's rule, so let's make a big space for the determinant, for the numerator and the denominator. Okay, so I look in I look at these two equations, and I need to put this in standard form, and that's pretty easy in this case because I already have the n's lined up in a column and the t's lined up in a column. I just need to move the constant to the other side, and there's only one constant in this problem. So I move this over, okay, and this becomes equal W, and W is 250 in this problem. Okay, so to find T, I substitute the solution vector, or the B vector, so that would be these two numbers, in for the T column. All right, so 250, 0 and 250, and then I take minus sine of 20 degrees, because that's just a number, and that's the coefficient in front of the first n. All right, then I take cosine 20 degrees, that's the coefficient in front of the second n, and then I just put, you know, the A matrix, the matrix of numbers for the unknowns. Okay, so this would be minus sine 20 degrees, cosine 20 degrees, cosine 20 degrees, and sine 20 degrees. Okay, so now at this point it's just a matter of taking the determinant. Okay, so I'm going to slide this over, give myself some room. Okay, so remember the determinant is given by this number times this number. All right, so that would be 250 times minus sine of 20 degrees minus this number times this number. Okay, but that number is 0. Okay, so 0 times anything is 0, and so that does it for the top. And then in the denominator, it's these two numbers multiplied together. So that would be sine times 20 degrees squared with a minus sign on it. And then we subtract these two numbers multiplied together. So minus cosine squared 20 degrees. Okay, so you can plug those numbers in your calculator, and what you get is, let me look it up. I got it, when I plug this in, I got 85.5 pound force for the tension in the cable. Okay, I put also the MATLAB solution for this, so you can see that as a reference, so that you can start to use MATLAB to check your work. So looking at the syntax of that, you can figure that out.